Oh gosh, what? Complex numbers can be matrices? But aren't complex numbers just like normal numbers, but there are two of them? And can matrices be complex, like having complex numbers inside of them? Well, hear me out. Hopefully I can give an argument that makes sense. So let's start with the basics of complex numbers. There are two components of a complex number, the real and imaginary, and we usually plot them out on a 2D graph, like this unit circle right here. On the x-axis we put the reals, on the y we put the imaginaries. And take this complex arbitrary number a. We can measure the magnitude of a with the Pythagorean theorem, and the angle of a with a little bit of trigonometry. And this makes sense when we plot a on a 2D graph. The angle is relative to the x-axis. One other important thing to note is that multiplying a complex number, like a, with I, will rotate a on the graph by 90 degrees, or pi over 2 radians. Actually, let's just take a moment to prove this rotation thing, since it turns out to be a crucial component of this whole matrix argument. I'll just take an arbitrary a as x plus yi. Multiplying by I gives us ia equals negative y plus ix. If multiplying by I rotates, we expect to see that theta a plus pi over 2 equals theta ia. And with a little bit of trig identity algebra, we can see that this holds when you wrap this equality in both sine and cosine. So we know that I has this rotation property. What other object, when multiplied, rotates a plane? A rotation matrix. Specifically, this matrix rotates by 90 degrees, and I'll call it J. J here is the equivalent of I, but represented as a matrix. And here you can see the analogous structure between multiplying with J and multiplying with I. It's just a different representation of the same operation. And there are more general rotations we can do than just 90 degrees, given by this matrix. This is what we're going to be using to represent general complex numbers. The magnitude of the complex number scaling its rotation from the real axis. Substituting the trig functions away gives us this elegant, simple matrix. Multiplying by it rotates and scales any vector space corresponding to multiplying by a traditional complex number. And you can see that for yourself with a little bit of algebra. Multiplying in Cartesian form, or multiplying in matrix form, gives exactly the same results. You just have to note that in matrix form, the real and imaginary components come from the matrix's first column. If you're interested in number theory, you'll only be satisfied if you see the whole list of necessary properties of a complex number proven. Most of them are just satisfied by normal matrix algebra properties, with the notable exceptions of multiplicative commutativity, that's a fun thing to say, and multiplicative inverse properties. Commutativity is maybe the first thing people learn doesn't hold for general matrices. Lucky for us, it does for our special complex matrices. You can see this by just doing the algebra, but it also makes sense intuitively. If you rotate a vector by 30 degrees and then 60 degrees, or the other way around, it doesn't matter. The other thing that doesn't hold for all matrices is the existence of an inverse. Generally, you can't divide matrices, but every non-zero complex matrix turns out to have a multiplicative inverse. I've written it down right here, and you can just check it by multiplying with the original matrix. Everything cancels out nicely to give us an identity matrix, which is the same thing as a complex one. This makes sense too, it's just rotating the other direction. If you're not convinced, try doing some of the algebra for yourself. Everything lines up very nicely to give us an elegant matrix representation for complex numbers. Thanks for watching, Hope you learned something new.